Maybe I can have a formal introduction. All right, welcome everyone. Welcome back to our seminar series on optimization algebra and geometry. We are pleased to have Professor Martin Helmer from North Carolina State University. Martin is going to talk about conormal spaces and Whitney stratification.
All right, thank you, Ali. And yes, thank you for inviting me. So yeah, as was mentioned, I'm going to talk a bit about Whitney stratifications and how we compute them. And that's where the conormal spaces will come in. And so our objects of interest are going to be algebraic varieties like this one here, which is the Whitney umbrella. So I'll just go very gently and won't assume a lot of background. So we'll say our objects of interest in particular are going to be singular spaces defined by polynomials. For example, these pictures below are two examples of this. And what we're going to want to do is stratify these spaces. So that means we want to separate them into smooth manifolds, which are going to join together in some sort of nice way, which we will make precise in a minute. Okay, so to be a little more mathematically precise, what we're going to look at are complex algebraic varieties. And actually, in fact, most of the things that I will tell you also work for real algebraic varieties. But I'm going to present things for the complex case just for simplicity. Okay, so our varieties are going to be usually called X, and it's going to be defined as a zero set of a list of polynomials as usual. And the point in a variety is going to be called singular if the Jacobian matrix of the defining equations drops rank at that point. Okay, so then given such an X, a stratification is going to be some filtration by closed subvarieties. So that if you take the union of all of them, you get X back, and additionally such that each thing that we'll call a strata, namely the difference of two of these successive varieties, is either empty or smooth, and also has pure dimension. So this will be, yes, either empty or it will be a smooth pure dimensional manifold. And additionally, we're going to want one more thing out of our stratification, namely we're going to want it to be Whitney to satisfy the Whitney condition. So there's classical work of people such as Whitney and also Tom and Hironaka that tells us that these stratifications are always going to exist for algebraic or analytic varieties, which was the work of Whitney, and then the semi-algebraic sets and sub-analytic sets was work of Tom and Hironaka. And so the place that we're actually going to end up is going to be a software package that will take an ideal and so take the defining equations of an ideal. For example, here is the defining equation of the Whitney umbrella, and you'll give it to the software, and it's going to spit out a stratification in this sort of form. So what that's going to mean is that the two-dimensional strata is just so it'll give us the closed sets, not the open sets. So this means that the two-dimensional strata is this whole Whitney umbrella minus the lower parts, right? So the one-dimensional strata is X equals Y equals 0. So that's just the Z axis, the purple handle. And the zero-dimensional one is just the origin. All right, so then the actual strata, the two-dimensional thing, will be the umbrella minus the handle. And then the one-dimensional strata will be the handle minus the origin. And then the zero strata is just the origin. Okay, so before telling you precisely what a Whitney stratification is. So if you already know that, well, sorry for being boring. But if you don't know that.
Sorry, one question.
Yeah.
I mean, can you tell me about the algorithm behind this Macaulay software? I mean, what kind of...
Yes, so that's what the talk is essentially about.
Okay.
And so yeah, the goal of the talk is to explain this algorithm is based on the paper that was that's linked to on the title slide. So I'll tell you how this algorithm works.
Okay. Perfect. Thank you.
Yeah. But before I do that, I'll tell you a little bit more about, in case for, to be friendly to everyone, I'm going to tell you a bit about what a Whitney stratification is precisely and why it's sort of an interesting thing to have. Okay, so I guess as a motivation, if you have a smooth manifold, say M, and you have 2 points P and Q in it, it's not too hard to show that there's a smooth diffeomorphism that's going to take P to Q. And you can do this, in fact, just by proving it for a unit ball in Euclidean space, and then essentially that will give it to you for any manifold. So the upshot of this is that if you have a point in such a manifold, and you gather together all of the diffeomorphisms and attack that point P with those diffeomorphisms, you get all of the manifold. Or in more formal terms, the action of the group of diffeomorphisms on the manifold is transitive. And you can also do this when you have a filtration. So in our context, that filtration is going to be the stratification X bullet. And we'll write this filtration as X bullet, where it's going to be a list of these Xi's, which are closed varieties, and the MI's will be these open smooth manifolds. And that will be where our diffeomorphisms act. And so then a filtered diffeomorphism is going to be a map homeomorphism from X to X, such that when we restrict each of these manifolds, we get a diffeomorphism. And these also form a group of filtered diffeomorphisms. And then one thing one might reasonably like to ask is that if we have some variety, we'd like to put conditions on how we build these MIs so that this group of filtered diffeomorphisms also acts transitively. That is, that if we have a point in each connected component of all of our strata, then, and we hit it with the group of diffeomorphisms, we generate all of the points in each strata. Okay, so I guess first we want to think a little about how we might subdivide a variety, a singular variety. And the first thing, which is quite reasonable, that one might think is, well, okay, I'll identify all the singular points, and that'll give me some variety. I know that I can particularly get this by taking minors of a Jacobian matrix. So this is another variety, and then I could look at that variety and find its singular points and so on. It's a reasonable thing to do. So this example will kind of show us why this isn't quite what we want. So this is called the Whitney cusp. And if we did this kind of procedure for the Whitney cusp, the singular locus is just going to be this black line, this black horizontal line where it sort of folds in on itself. Okay, so it's a line, and the line is about as smooth of a manifold as you can have. But if you look at the central point on this line, so let's say this red dot here, if we just zoom in on that line, it turns out that a neighborhood of that point is sort of different from neighborhoods of any other point on this black line. And in particular, if you actually act with our diffeomorphism group on this central red point, it just all of the diffeomorphisms will fix that point, right? So that means that if you include that red point in the black line, you don't have a transitive action of the diffeomorphism group. So it's breaking the property that we were sort of hoping to have. Okay, so now let's define the condition that we actually want to have, the Whitney condition, which will let us in particular have this nice filtered diffeomorphism transitivity that we would like. Okay, so as before, X bullet's a filtration, and the M's are the strata. Okay, so then what is a Whitney stratification? Well, we want all of the strata to satisfy a condition called condition B. And so for any two strata, let's call them sigma and tau. So for sigma, I would like you to we'll think of everything on this picture of the Whitney cusp. So for sigma, I'd like you to think of this red the red two-dimensional strata. So basically the Whitney cusp without the black line, that is sigma, and tau is the black line. So it's what we should have in mind. And then X, of course, is the whole variety, the Whitney cusp. Okay, and so the condition that we want for any point on the black line, so any point Y and tau, is that if we take two different sequences, both of them converging to Y, so we'll take one sequence in sigma, so that's this blue sequence along the top, for example, that it converges to, let's take Y to be the central red point, because that's the interesting one. So this blue sequence converges to the red point. Then we'll also take another yellow sequence of yi's in tau, so inside the black line, also converging to the same red point. So if Whitney's condition were to hold at this red point, then what we would require is that if we take all of these secant lines between the blue and the yellow points, and then we take the limit of those secant lines as it goes to our point of interest, y, that limiting secant should lie inside the limiting tangents of all of these, the limiting tangent plane of all of these blue, of this blue sequence, right? So here we see that does not happen. In particular, the blue sequence, the limiting tangent is the XY plane, whereas the secant lines actually give us the Z-axis. So it's not only not contained in the plane, it's actually completely orthogonal to it. Okay, so that in particular means that we would need to move that red point out of the black line when we're doing the stratification, because condition B doesn't hold there. Okay, so we have a nice analytic and geometric description of condition B, and there's a theorem that tells us that implies this transitivity of the diffeomorphism group, which is one of the nice things it does. There are others, but it's just an example. But what we'd like to do is, if someone hands us the equations for the Whitney cusp or something else, we'd like to find the equations of all of these xi in this filtration. Right, so we would like to do this automatically. And limits of sequences are not the most manageable for that. So we need a new way to think about this. Okay, so our first ingredient in that direction is going to be the conormal space. So I'm gonna just restrict myself for now to projective varieties, complex projective varieties. Everything holds in actually for real affine varieties, though that's more recent and that isn't in the paper, but I'll come back to that a little bit later. But we'll stick to this case because it's a little cleaner to talk about. Okay, so we'll take X to be a projective variety, then we're going to write Pn star for the dual projective space. So points in the dual projective space are hyperplanes in the projective space, right? So then we're going to define this thing called the conormal space. And we're also going to write X reg for the smooth, all the smooth points in X. So what the conormal space will do is for each smooth point P in X reg, we're going to pair that smooth point with some xi that contains so this is a hyperplane in Pn, represented as a dual point. So we'll pair it with each hyperplane that contains the tangent space at that point, right? So there's could be many of these hyperplanes. So there, their P could be paired with several hyperplanes. And then we'll define a conormal map, which is just going to be a projection, namely the coordinate projection from Pn cross Pn dual back to Pn, and then that induces a projection on this conormal space back to X. And so, yeah, for the fiber of a point under this map is just going to catalog all of the either hyperplanes or limiting either the tangent hyperplanes or the limiting tangent hyperplanes of the point, right? So for example, for this picture here where we have this X, we take a smooth point on this curve. The fiber is just going to be, well, it's going to not just be the plane, it'll be the pair of the red point and the and the tangent plane together. And then the fiber over the blue singular point is going to be the two limiting tangent planes, both paired with that same point. So the one that limits coming from this direction and the other that limits coming from the other direction. Okay, and we have one more ingredient, which is fairly standard fare for commutative algebra, but again, just try to introduce things so everyone is familiar. So given an ideal in a polynomial ring, we can compute a primary decomposition. So that is, we write I as the intersection of some list of ideals, each of which is primary. And that just means if we have a product of two polynomials in the primary ideal, then either one of them is in it or a power of the other one is in it. And to each primary ideal, there's an associated prime, which is just the radical of the primary ideal. And the set of associated primes is the unique sort of geometric objects that we have here, and the primary components actually are not unique. So that's, I think, the main takeaways here. And here's just an example of a primary decomposition. I think one of the favorite ones that sort of illustrates this, where you decompose this ideal xy comma y squared into y intersect x y squared. Right, so geometrically, you have a point embedded in the line as your primary decomposition. And our associated primes are both the point and the line. Okay, so then now I'm going to give an algebraic criterion for Whitney's condition B. So we'll take X to be a pure dimensional variety, and Y will be some subset of its singular locus. It'll be non-empty and irreducible subvariety in the singular locus. And we want a theorem that's going to identify all points in Y where condition B fails with respect to X. Okay, so we'll define a couple things. We're going to define this fiber ideal, which is just going to be the ideal of the conormal map, which I'll in the next slide tell you how you would get. And then the ideal of we could just even say Y is the singular locus if you like. So the ideal of the singular locus. And then what we want to do is take a primary decomposition of this ideal. And that's going to give us a bunch of primary components in this product of projective spaces. Or geometrically speaking, right? It's in this, remember if we go back to this thing, our conormal space is in a Pn cross Pn dual, right? So this ideal is in the coordinate ring of Pn cross Pn dual. So in twice as many variables. And we'll take a primary decomposition there. And then what we're going to do is we're going to look at all of the components of this primary decomposition that when we project them back to Y under the conormal map, we get something of dimension strictly less than Y. So we get a proper subvariety of Y. And remember, Y is irreducible, right? So having dimension less than Y is really just equivalent to being a proper subvariety of Y under this projection. And we collect all those together along with the singular locus of Y. And those are precisely the points where, or I guess these all points where condition B fails are contained in the set A is the right way to say it. And so then in particular, if we pair the smooth part of X with Y minus A, then that pair is going to satisfy condition B. And this is going to be how we actually build an algorithm to stratify things.
Sorry, can you explain the difference between Y singular and Y? So what is Y singular?
So Y singular would be the singular locus of Y.
Okay, so Y itself is the set of singular points of X.
Yeah, and
Y,
it could it could have some singular points itself, you know, as a variety itself.
Okay, right.
So it's saying we'll take those singular points, but then we'll also take, so for example, in our Whitney cusp example, the singular locus was empty of y because y was just that line, that black line. So it didn't have any singular points of its own. So the only things of interest come in this first set here. But you could have the case where y maybe had its own cusp or something inside it, and
right.
So we'll add that in addition to these other points, which are possibly smooth points of y.
Okay, thank you.
Yeah. All right. Yes. So this gathers together, in particular, all of the, and that's the important point, that in a computable way, we've characterized all of the points where condition B can fail, and we can actually write down equations for all of these things. In particular, singular loci, we know how to compute just by taking the minors of a Jacobian matrix. And this ideal of this fiber, well, that's just an ideal, and I'll just in the next slide show you how you get the ideal of the conormal space. And then a primary decomposition we can compute. So actually, and actually, we don't, strictly speaking, need the actual primary decomposition. The associated primes are enough because we just need to check dimension, and a primary ideal and its radical have the same dimension. So, okay, so then how do we get this conormal ideal? Well, if X is in Cn and has, let's say, pure dimension K, and it's defined by equations F1 through Fr, and Y, say, is our subvariety of X, then we're going to be working in the ring. Let's say that on the primal space, we put the variables X, and on the dual space, we put the variables Xi. Then the ideal of the conormal space is just going to be the n minus k plus 1 by n minus k plus 1 minors of the Jacobian matrix augmented with the variables of the dual space. And then I forgot to add it here, but we should also saturate out the singular locus from that ideal, actually. But in any case, we can do that.
Sorry, where does this ring come from? The X and Xi, I mean.
Oh, yes, so that comes from, if we go back to where we defined the conormal space, it's the coordinate ring of this product space, right? So the X's are the variables of the primal space, and the Xi's are the variables of this dual space.
Nice, thank you.
Okay, so yeah, the main takeaway here, I guess, is that we have all the information then we need to compute the subvariety A of Y, where condition B fails. Namely, we can compute this conormal ideal, and then what did we need to compute? Well, we needed to compute that, and Y is an input itself, so then we just need to do this conormal ideal computation and then a primary decomposition, or at least an associated prime computation. So let's actually sort of try to write out what the algorithm looks like a little bit to be very precise. Okay, so we start with an ideal Ix defining a variety of dimension K. And we want to find all points where condition B fails. So the way that we're going to do that is we'll first take Y1, let's say, as the singular locus. So we'll compute the maximal minors of the Jacobian matrix of the defining equations of X, and take the radical of that ideal. So the n minus k by n minus k minors of the Jacobian. And then we take the radical, and that will define the singular locus. And then we use that as the Y in our theorem, as our first candidate Y. So we compute this fiber ideal and its primary decomposition. And then the theorem tells us that condition B will fail on this set Y2, which is collect, which we get by taking the singular points of y1, it should be y1 thing here, together with all of these points that you get by projecting primary components that project a strictly smaller, a space of strictly smaller dimension than whatever the dimension of our singular locus was. And then you'll just repeat this again with y2. And you have to drop dimension by at least 1 because singular locuses are always proper codimension, like have strictly less dimension than the ambient space. So you will eventually run out of places to go, and that will be your stratification. Okay, so that actually, if you put this together, then you get an algorithm to this, or essentially this is how the Macaulay code that I showed early on, this is what it's doing.
So sorry, you assume that X is irreducible also?
Yeah, we don't need to, but
because you keep working with the singular points, right? So you must have a finite. Right?
Yeah, so if X is not irreducible, you can just take an irreducible decomposition and apply procedure to. Essentially, the theorem requires pure dimensional. So if it's just pure dimensional, you can actually just do things without doing an irreducible decomposition. But if it's not pure dimensional, then you should decompose it before proceeding.
Okay.
So the software will accept any sort of input and check all these things, but yeah. Theoretically, in the theorem, it would be for a pure dimensional X. And so I think it was a half-hour talk. That's what I planned anyway. So is that right? Yeah. So I think that's about right. This is my last or second to last slide. So we also, I guess, in the paper, extend this to maps. So if you have a map, a proper map F between two varieties X and Y, then we also give an algorithm to stratify F, by which we mean find Whitney stratifications of X and Y so that every strata S of X, or that for every strata S of X, the restriction of this map to S is a submersion, mapping into a strata of Y. So I guess what the most interesting upshot of such a stratification is that if you have some strata of Y, so the codomain, if we have some strata, let's say N of Y of the codomain, and we take 2 points, Q and Q prime in that strata, then the fibers of both of those points have the same homology groups. And so like they're topologically identical, essentially. They have same Betti numbers, same homology groups and everything. So it gives us a way to subdivide the codomain into pieces where we can be sure that the fibers over any point are sort of going to give us something topologically similar. And we also give an algorithm to do this. I won't discuss it now because it's a little bit messy, but it is there in the paper if anyone would like to read about it. And so just to wrap up, we talked about an algorithm to compute a Whitney stratification of an algebraic variety X in Cn, and we also have a map also have an algorithm in the paper to stratify maps between varieties. And then the paper is only for complex varieties, but in recent work, also with Nanda, we've extended this to real varieties as well. So we have a fairly similar algorithm that will also do both maps between real varieties and Whitney stratifications of real varieties. And there's a software package for Macaulay 2 called Whitney Stratifications that implements the things in the paper. And that's it.
Thank you, Martin, for this fantastic talk. So I guess we don't have any other audience to questions, so maybe I can ask my question. So my first question is about the algorithm itself. So this is So if we think of every step as if we think of implementing every step symbolically, right?
Yeah.
So what would be, and of course you have like the degree of polynomials, you have the dimension. What is the worst case complexity for this procedure?
I mean, it's essentially the worst case complexity, and I mean, this is always sort of a discussion with, it's based on a Grosvenor basis calculation, right? So the worst case complexity is always something of the form like d to the 2 to the n. So it's like double a exponential and n. So I mean, like on paper, the complexity is similar to, you know, like Grosvenor basis and CAD and all these things have the same complexity. But I mean, in practice, Grosvenor basis is able to compute a lot of examples that are just, you know, not really feasible for things like a CAD. So yeah, I mean, the complexity is in practice similar to a primary decomposition of an ideal. So
right.
Grosvenor basis computation.
Right. So, so I mean, if we consider a complex variety and we think of it as a semi-algebraic set by identifying every complex number using its real part and imaginary part,
yeah,
and then we just use cylindrical algebraic decomposition, which I think is the only option we have here. So, I mean, what would be? So I guess I need to put the question that way. So what is the difference in terms of technicality if we just think of the whole complex variety as a semi-algebraic set and just give it to cylindrical algebraic decomposition? How do we get? Do we still get? I mean, how do we need to modify the cylindrical algebraic decomposition to get the Whitney stratification? Well,
so
I mean,
yeah, there is like there was a paper. I think this was, as far as I know, there's I think 2 other papers that had looked at computing Whitney stratifications in an algorithmic way. And I think the first one was something from the late 80s that essentially just described how you would encode Whitney's conditions as a quantifier elimination problem, and then you could apply CAD to that in theory. But in practice, if you do that, it won't even be able to stratify the Whitney umbrella. So, you know, in theory, you can get, yeah, even like if you use like imaginary, I mean, maybe I shouldn't say that, but like these like critical point methods and things like this that hypothetically exist but aren't implemented, you might get slightly better theoretical complexity by thinking of it as a CAD problem. But in terms of actual practical computation, the Grosvenor basis based way is much more feasible.
Okay, right.
So yeah, I mean, like all of these things can be done with a CAD in theory. It's just that in practice, it doesn't terminate, even on
right.
you know, really easy examples.
Right. And I guess my last question is about like the connection to the stratifying Morse theory and the work of Goreski McPherson. So does this theorem has anything to do with this stratifying Morse theory or?
Yeah, I mean, well, I guess the Whitney like Whitney stratifications are sort of ubiquitous in stratified Morse theory, right? They basically assume left, right, and center that you can construct stratifications for, you know, this or that objects. And that was actually part of our motivation for constructing this algorithm, was to be able to actually kind of implement some of the ideas in stratified Morse theory more explicitly. Because often a basic precondition for that is having a Whitney stratification. So yeah, in that sense, I think it's strongly related. And in fact, this idea of stratifying a map is also heavily, that comes from Goreski and McPherson, it's their definition. So it's sort of from stratified Morse theory. And and it's used sort of heavily in their book.
Okay. All right. All right. Thank you. So I guess there is no other question because there is no one else is here. But thank you very much again for accepting our invitation, and I hope to see you soon in a future event.
All right, that sounds great. Thank you. I'll just stop the sharing.
Thank you. And let me just stop recording.